Okay, in this section, we are going to formally study the functions of inverse sine, inverse cosine, inverse tangent, etc. So let's just recall the basic behavior that we understand about these functions. So we know, for example, that sine of pi over 3 is equal to rad 3 over 2. Okay, and we understand that the trig functions, the direct trig functions, sine, cosine, tangent, cosecant, etc., they take as input an angle, and in this case we have an angle in radians, and they generate as output a ratio. For instance, the ratio of two sides of a triangle. And we have seen that the inverse trigonometric functions, which are written this way, they do exactly the opposite. They take as input a ratio, and they generate an angle as output. So they are a way of kind of undoing the actions of sine, cosine, whatever, right? But we saw that these functions may have a little bit of unpredictable behavior, because we also know that sine of 2 pi over 3 is rad 3 over 2. And yet, inverse sine of rad 3 over 2 will never give you 2 pi over 3. It will always just give you pi over 3. So it's not necessarily a faithful reverse engineering of an equation like this. And what we're after is exactly what is the driving behavior behind these inverse trigonometric functions, so we can work with these functions. So let's recall the graph of y equals sine x. All right, so here we are. So when we say something like the sine of pi over 3 is rad 3 over 2, what this means is if you locate pi over 3 on the x-axis, which is, say, right here, then the corresponding y value on the function is rad 3 over 2. And when we say that the inverse sine of rad 3 over 2 is pi over 3, we're just going the other way. We're saying we'll start with the ratios, which are along the y-axis, and locate rad 3 over 2, which is right here, and it corresponds to an original angle of pi over 3. The problem is that there are many angles, for instance 2 pi over 3, whose sine value here is rad 3 over 2. And it's not just those two. We could go all the way out here, and then there's another pair. Or we could go out toward the left, and we'll hit another pair. And in fact, there's an infinite number of these pairs. All right, so what do we do about that? Well, the issue is that sine of x, and indeed all of the trig functions, fail what is called the horizontal line test, and they fail it spectacularly, which means for any given y value, there's not one x value, there's not two x values, but there's an infinite number of corresponding x values. So, the way we solve this problem is by agreeing that if there's a solution in the first quadrant, we will always go with that, which means this piece of the curve is going to get included in the definition of inverse sine. So that means if we choose something like rad 3 over 2, we're not going to worry about the piece over here or the piece over here or the piece over here. We're only going to worry about the piece that's right here. And we're going to consistently get our correct answer of pi over 3. Inverse sine of rad 3 over 2 is pi over 3. But what about if we asked, what is inverse sine of negative rad 3 over 2? We have the same problem, which is that there's an infinite number of candidate solutions. Okay, no problem. We will just decree this other section here. So that means that the correct answer will be negative pi over 3. So we define y is equal to inverse sine of x. To be clear, this x and y are not the same x and y from the graph. In this statement, x is a ratio. We know inverse sine of a ratio will generate an angle y. So y is going to be some angle, like pi over whatever. And in our graph, x is the angle and y is the ratio. So we've swapped the role here. Well, this is defined to mean that x is equal to sine of y. Remember, x here is the ratio and y is the angle. And trig functions take angles and generate ratios. But it also means that the angle, which in this case is y, is between negative pi over 2 and positive pi over 2. All right, let's see how this plays out from the graph of y equal cosine of x. All right, of course we can see that the graph of cosine fails the horizontal line test spectacularly. And we want some consistent rules. Well, if we plug a positive ratio in, we want something from the first quadrant again. This is 0 to pi over 2. If we plug a negative angle in, we have the choice of either going over here or going over here. But of course, we can probably see that it just makes more sense if we choose this part over here. So this means we define y equals inverse cosine to mean that x is equal to cosine of y, and the angle, which is in this case y, is between 0 and pi. Okay, so we're starting to see that the range of these inverse trig functions depends on which inverse trig function we're using. So for inverse sine, the range is negative pi over 2 to positive pi over 2. And for inverse cosine, the range is 0 to pi. So let's do this one more time with the graph of tangent. And then let's summarize all this information in a nice, useful table. Okay, well, we know that tangent has asymptotes at the odd multiples of pi over 2, and that tangent has x-intercepts at multiples of pi. And it basically takes on this shape. Okay, so again, we're looking for a proper definition of inverse tangent. So if we choose a positive ratio, we want a consistent way of dropping down to get an original angle from that. Well, I think we can all agree the best choice, once again, is to choose the first quadrant here. So if you choose a positive angle, you drop down into a first quadrant angle between 0 and pi over 2. Okay, what if we choose a negative angle? Well, once again, I think we can all agree that the best choice is to use this limb down here. So this wasn't too hard to work out. So let's define inverse tangent. So we'll say y is equal to inverse tangent of x means that x is equal to tangent of y being the angle in this case, and the angle is between negative pi over 2 and positive pi over 2. Okay, so before we summarize all this information, let's just get a quick word on notation here. So if we have something like inverse sine of x, this is also denoted as arc sine of x. All right, inverse cosine of x is also denoted arc cosine of x. Inverse tangent of x is also denoted arctangent of x, etc. All right, while we did not investigate these last three graphically, we're still going to compile everything into a single table that's easy for us to reference. So if you encounter this, y equals inverse sine of x, which is the same as y equals arc sine of x, this is the same as the following statement. X is equal to sine of y, and y is between negative pi over 2 and positive pi over 2. Now, we're going to do this for all 6 trig functions and this particular range of the function, right? These are the outputs of the inverse trig functions, can probably be easier reckoned in terms of quadrants. So the interval negative pi over 2 to positive pi over 2 constitutes quadrant 1 and quadrant 4. And we're going to see that all of these inverse trig functions will come with a range that's quadrant 1 plus some other quadrant, and that other quadrant will either be quadrant 2 or quadrant 4. So for inverse cosine, which is also written as arc cosine, this is equivalent to x equaling cosine of y, and as we saw, the angle y is between 0 and pi. That corresponds to quadrant 1 and quadrant 2. For inverse tangent or arctangent of x, this is equivalent to x equaling tangent of y. And as we saw, the bounds of the angle y are between negative pi over 2 and positive pi over 2. So that corresponds to quadrants 1 and 4, just like inverse sine. All right. For inverse cosecant or arc cosecant, this is equivalent to x equaling cosecant of y. And inverse cosecant will inherit its behavior from inverse sine. So again, we're going to be quadrants 1 and 4. Inverse secant will inherit from inverse cosine. So that's quadrant 1 and quadrant 2. And finally, inverse cotangent or arc cotangent means that x is equal to cotangent of y. And now you might think, well, inverse cotangent will just inherit from inverse tangent. But actually it doesn't this time. If you think about the graph of inverse cotangent, it actually has an asymptote right here at 0, and it has another asymptote right here at pi. And there's one perfect swoosh like this between 0 and pi. So that's actually what we would grab from both quadrants 1 and 2, which are all the angles between 0 and pi. So this one is the exception to that pattern. So that's quadrant 1 and quadrant 2. If the ratio is positive, meaning if x is positive, then you're guaranteed to get output in the first quadrant. That is the easy case that doesn't require really any thought. just go for the simple version of the angle from the first quadrant if you're given a positive ratio. If x is negative, meaning you're giving a negative ratio, that's when this auxiliary quadrant will be used, and it's either quadrant 2 or it's quadrant 4. 3 of them are quadrant 2 and 3 of them are quadrant 4. All right, so how do we tell which ones are quadrant 2 and which ones are quadrant 4 at a glance? Just look at the middle letter of the trig function. If it's O or E, as in cosine, secant, or cotangent, then the auxiliary quadrant is quadrant 2. Otherwise, it's quadrant 4. I typically simply refer to that as just the OEO rule. Okay, let's look at some examples of using these functions. Okay, so to start, we're going to do some evaluations here. So let's evaluate arcsine of rad 3 over 2. Well, we already did this at the beginning of the lecture, but now we have more mechanical ways of approaching these problems. So the suggestion here is to introduce an angle, like say y or theta. We'll go with theta. So theta is arcsine of 3 over 2. Well, what does that mean? That means that sine of theta is equal to rad 3 over 2. And theta is in the first quadrant. Now, why do we know theta is in the first quadrant? Well, that's because this ratio was given as positive. So regardless of what the inverse trig function is, when you have a positive ratio being plugged in, you're going to get a first quadrant angle. So all we have to do is think of what first quadrant angle has a sine value of rad 3 over 2. So this does depend on good knowledge of the unit circle or triangles. And in this case, we're going to say pi over 3. And unless the context specifically specifies degrees, we're going to assume these functions are always working in radians. So the answer is pi over 3, not 60 degrees. All right, let's evaluate inverse sine of negative 1/2. Well, we're going to be doing what we've been doing. So we'll let theta equal inverse sine of negative 1/2. And what does that mean? That means that sine of theta is negative 1/2. And theta is in quadrant, well, the input here was negative, which means it's not going to be quadrant 1, it's going to be the auxiliary quadrant associated with inverse sine, which is either quadrant 2 or quadrant 4. So which one is it? There's that mnemonic, what's the middle letter here? If it's E or O, then the auxiliary quadrant is quadrant 2. And it's not. The middle letter of sine is I, which means this must be a quadrant 4 angle that we seek. So therefore, theta is whatever quadrant 4th angle we can think of has a sine value of negative 1/2. So that would be negative pi over 6. Now, you may be tempted to write 11 pi over 6. That would be incorrect. When we're referring to quadrant 4 here, we're meaning the negative 4th quadrant angles because of this segment of the sine curve that we grabbed, which was to the left of the y-axis. So these are negative values here. So it's incorrect to say 11 pi over 6, even though sine of 11 pi over 6 is negative 1/2. That's not what inverse sine of negative 1/2 is. Okay, what about inverse sine of rad 2? Well, let's do what we've been doing. We'll let theta be this unknown angle, inverse sine of rad 2. And what does that mean? It means sine of theta equals rad 2. And theta is in quadrant, in this case, it's easy, quadrant 1, because rad 2 is a positive ratio. So to answer this question, we just have to think of what angle theta has a sine value of rad 2. Now, this particular theta value doesn't exist. Rad 2 is about 1.4, which is greater than 1, and we know that the output of the sine function is always between -1 and +1, which means there's no such theta value. And our conclusion is that inverse sine of rad 2 is undefined. Okay, evaluate arc cosine of 0. So what we're going to do is, of course, we'll let theta equal arc cosine of 0. And what does this mean? This means that cosine of theta is equal to 0. Well, 0 is not positive or negative, so we can't really pin down a quadrant here. But this does mean that the answer will be quadrantal. So just ask yourself, can you think of an angle whose cosine is equal to 0? And what's like the simplest version of that angle? Pi over 2. And if you think about the range of the inverse cosine function, which is 0 to pi, pi over 2 is right in the middle of that range, so this is perfect. All right, what about inverse cosine of -1/2? So again, we're going to let theta be inverse cosine of -1/2. And that means that cosine of theta is equal to -1/2. Okay, what quadrant are we predicting that theta will be in? Well, this input is negative, which means it'll be the auxiliary quadrant, not quadrant 1, but quadrant 2 or quadrant 4, the one associated with inverse cosine. So which one is it? Well, let's use the OEO rule. The middle letter of cosine is O. Okay, well that means it's quadrant 2. So what quadrant 2 angle has a cosine value of -1/2? Well, that would be 2 pi over 3. Okay, what about arctangent of rad 3? Well, once again, we'll let theta be arctangent of rad 3. And what does that mean? It means that tangent of theta is equal to rad 3. And what quadrant is theta in? Well, this is the best case scenario. If the ratio is positive, then the output angle will be in the first quadrant. So we just have to think, what angle in the first quadrant has a tangent value of rad 3? Oh, the answer is pi over 3. And hopefully you're starting to appreciate how implicit knowledge of the unit circle really helps you work out problems like this. Okay, one more of this particular brand. So inverse cosecant of -rad 2. Well, let's let theta be that thing. What does this mean? It means cosecant of theta is equal to -rad 2. And it means that theta is in quadrant what? Well, the ratio given was negative, so that rules out quadrant 1, which means it's going to be quadrant 2 or 4. And the middle letter of inverse cosecant is not O or E. That means that quadrant 4 is the quadrant we seek here. So our theta will be a quadrant 4 angle. And to be specific, it'll be a negative quadrant 4 angle, which is actually easy because you just think of the first quadrant angle and you throw a negative in front of it. So what angle has a cosecant value of -rad 2? Well, that's like saying what has a sine value of -1 over rad 2. Well, that would be -pi over 4. Okay, the remainder of the examples will be of the form of a trig function composed with an inverse trig function. And every time you have a trig function composed with an inverse trig function, it will reduce. So what is this going to reduce to? Well, the trick is identifying the angle in the problem, and that would be, in this case, the inverse sine of 2/3, right? 2/3 is a ratio. The inverse sine of 2/3 is an angle, and we're looking for cosine of that angle, theta. So essentially what we're doing is we're saying let theta be inverse sine of 2/3. What does that mean? That means sine of theta is equal to 2/3, and theta is in quadrant, well, because this is a positive ratio, we know theta is in the first quadrant. So this problem is basically like saying, find cosine of theta. If you know sine of theta is 2/3 and theta is in quadrant 1. Yeah, we've answered lots of problems like that. Best way to do it is probably just to draw a triangle. So sine of theta is 2/3. Well, let's label the opposite and the hypotenuse as 2/3, like so. And we'll use the Pythagorean theorem to find this missing side. So we know that b squared plus 2 squared is equal to 3 squared. So b is equal to the square root of 5. Okay, here's the original question, cosine of inverse sine of 2/3, which we know is cosine of theta, of course, because we decreed that inverse sine of 2/3 was theta. What's cosine of theta? Well, we'll read it right off the triangle. Adjacent over hypotenuse. So that would be rad 5/3. And it's positive because theta is in the first quadrant. So there it is. Okay, here's another one just like that. Cosecant of inverse cotangent of some ratio. So again, it's trig composed with inverse trig, which we know will always be something. And we're going to do what we do, which is we'll let theta be the angle in the problem. So that's going to be let theta equal inverse cotangent of -15/8. And what does that mean? That means that cotangent of theta is -15/8. And theta is in what quadrant? Well, it won't be quadrant 1 because this ratio is negative. So using the OEO rule, we can see, well, the middle letter is O. So, second quadrant. So theta is in the second quadrant. So what are we after? We're after cosecant of theta. And we know what cotangent of theta is, and we know what quadrant theta is in, so we have everything we need. So cotangent of theta is -15/8. We'll just label this 15 and this 8 because on a triangle everything's positive. The cotangent, of course, being adjacent over opposite, informed the choice of where to put the 15 and the 8. So what are we after? The hypotenuse. So 15 squared is 225, 8 squared is 64. So c squared is 289, and the square root of 289 is 17. Okay, well here's the original question. Cosecant of inverse cotangent of -15/8. Well, that's cosecant of theta, the way we defined theta. And we know that cosecant of theta can be read off this triangle. Cosecant is hypotenuse over opposite. So that would be 17/8. And we should assign the correct plus or minus here based on the quadrant of theta. Theta is quadrant 2. Cosecant's positive in quadrant 2. So we'll keep this positive. Okay, for this particular one, we are evaluating sine of arctangent of 4/3 minus arccosine of 12/13. So we're going to proceed as we have been doing, except this time we have two angles because each of these little pieces generates an angle. So let's call them angles A and B. So specifically, we're letting A be arctangent of 4/3. Okay, that means that tangent of A is equal to 4/3, and A is in quadrant 1 because 4/3 is positive. All right, we're going to need a triangle, so why don't we just quickly draw one right here. So we know that tangent of A is 4/3. Tangent is opposite over adjacent. So there's our 4/3. We can use the Pythagorean theorem to find the missing hypotenuse, which in this case will be 5. It's a 3, 4, 5 triangle. Now we can read sine, cosine, tangent, whatever we want of A just by pulling it off the triangle. Okay, let's do the same thing for B. B is arc cosine of 12/13. This means that cosine of B is 12/13, and B is also in quadrant 1, again because the 12/13 is positive. So we'll get a triangle here, and let's label the sides. Cosine is adjacent over hypotenuse, so we'll put a 12 and a 13 there. And again, using the Pythagorean theorem, the missing side will be 5. This one's also a famous 5, 12, 13 triangle. All right, so let's go back to the original question here. We are after sine of this stuff. So, of course, that's sine of A minus B, according to our labeling that we've done. Well, we know just what to do with that. This unwraps to sine, cosine, cosine, sine. So we're just going to work out each of these individual pieces using the triangles that we have. So we can see sine of A is 4/5. Cosine of B is 12/13. Cosine of A is 3/5. And sine of B is 5/13. So this is 48/65 minus 15/65, which is 33/65. So there it is. Okay, so we're going to continue evaluating these trig functions composed with inverse trig functions. But notice now we don't even have a specific ratio, we just have a variable x. And whenever you have a trig function composed with an inverse trig function of a variable, it will always reduce 100% of the time. Doesn't matter which trig function this is and which inverse trig function this is, this will always reduce to something purely algebraic, something that doesn't show any indication that it's related to trigonometry. So how do we do that? Well, exactly the way we've been doing it. We're going to call the angle here theta. So we're going to let theta be inverse secant of x. And what that means is secant of theta is equal to x. Now, because x was given to be positive, we know that theta is in the first quadrant. Okay, so what are we after? Well, we want cotangent of theta, and we're given secant of theta. So we are going to draw a triangle like we always do here. Secant of theta is x. Now secant concerns hypotenuse over adjacent. So it might help to write this as x/1, and this will tell us how to label the sides of the triangle. So the hypotenuse we can label as x, and the adjacent as 1. So indeed, secant of theta is x/1. Using the Pythagorean theorem, we can find this missing side here. We'll call it a. So we can see that a squared plus 1 squared is equal to x squared. So a squared is x squared minus 1, and therefore a is the square root of x squared minus 1. Okay, so we have all three sides of this triangle in terms of x, and that means we can find sine, cosine, tangent, whatever, of theta. So specifically, what are we after? We want cotangent of inverse secant of x. Well, that's cotangent of theta, and cotangent is adjacent over opposite. So this is going to be 1 over a, which we calculated to be that. So this is the algebraic expression that's equivalent to cotangent of inverse secant. Okay, same kind of story here. Trig function composed with inverse trig function. This time we do have a little 2 here to worry about. We'll deal with that in a minute. Let's let theta be the angle here. So we're going to let theta equal inverse cosine of x. And that means that cosine of theta is equal to x. And also because we're told that the ratio is positive, that means our theta is in the first quadrant. Very nice. All right, we know we're going to need a triangle, so let's just draw that right now. We are told that cosine of theta is equal to x, so let's think of that as x over 1, and cosine is adjacent over hypotenuse. So we're going to put an x here and a 1 there, and again we will look for this missing side here. We'll call it a. So we know a squared plus x squared is equal to 1 squared. So a squared is 1 minus x squared, and a is the square root of 1 minus x squared. Okay, so now we can read sine, cosine, tangent, whatever, off of this triangle. Very good. Let's go back to the original problem and see what we have. We have sine of 2 inverse cosine of x. That's where we started. That is, of course, sine of 2 theta. Okay, well, we know what to do with sine of 2 theta. That is a double angle, and we have the identity that sine of 2 theta is 2 sine theta cosine theta. So we can use the triangle to work out sine of theta and cosine of theta, and then we'll be done. Sine of theta is, of course, opposite over hypotenuse. So that would be opposite over hypotenuse. And cosine of theta is adjacent over hypotenuse. So that's x over 1. Okay, let's clean this up a little bit. We're going to see we get 2x rad 1 minus x squared. And there it is.
Well, there it is.